Hello viewers and my dear students. Welcome to one-dimensional problem analysis. This is in fact problem 3 on one-dimensional bar analysis. I am giving you a demo on one-dimensional bar analysis with two materials fixed at both the ends and with an axial load at the center. And the problem will be this way. Okay, the problem is this. In the problem 1, this is problem 3. This is problem 3. In problem 1, it was only fixed at one end and at the free end there was load. Now in this problem I have made a small change. It is fixed at here as well as the end. That means it is fixed at both the ends and you have an axial load at the center. This has a different cross section. This has a different cross section. Please understand, this has a cross section of 2400. This has a cross section of 600 mm square and this has a length of 300. This has a length of 400, and also you should know this is aluminum with Young's modulus as 70 into 10 to the power of 9 Newton per meter square. Now since everything we do it in mm, we'll have this also in mm only. In that way, E1 will be aluminum. Aluminum Young's modulus will be 70 into 10 to the power of 3 I'll take Newton per millimeter square. In the same way, for steel also I'll take 200 into 10 to the power of 3 only Newton per millimeter square. In that way, I'll complete the problem. Now we'll go for answers. Okay. Now you see here, in this way I have already changed. I changed the job name, Gurdat problem 3 one dimensional. I have new log and error files. I have made it ready. Okay. And I'll also change the title also. Change the title. Problem 3 one dimensional analysis. This already has come. If you see the log file also, okay, this has come, one dimensional analysis and all that, it has come. Okay, now you see here, we'll start doing preferences, structural, okay. Then preprocessor, element type, add, edit, delete, add, link element you do, same link 180 you choose, link 180, you just say close. And the real constant, you have two real constants. As you see here, first one is add, the first one is real constant of, this is aluminum 2400. This I've shown you already, just see the problem, 2400. This you apply. And the second one has a real constant of 2, that is 600 mm square. Second one is 600 mm square. In that way, two real constant I have named. Okay. Then two materials also. Material properties, material models, structural, linear, elastic, isotropic you take. First material is aluminum. I have told you we'll have it in consistency in units here. 70 E3 you take. 70 E3 because there is a Newton per millimeter square. Just say okay. Okay. Then material, new model you take, then you say the second material. The second material, as you know, it is steel. It is, they are given 200 E3. 200 E3 you take, okay. Just say okay. And material exit. That means, as you know here, there are two materials, as I told you. This is, I have already added 2400, 70 E3. This is 600, 200 E3 I have put. Now I'll start doing the model. This is 300, this is 400 and all that. We'll do this. Okay. Now see here, I'll do that modeling. Create key points in active coordinate system. 1 you take, 0, 0, 0. Okay. Apply you do. 2 you take. 2 is, as you know here, it is 300. 300, 0, 0, you take, 3 you take, 3 you take, 3 is, it is 4, that is 700, 300 plus 400, 700, 0, 0. Okay, let's say okay. That means I have created 3 key points. As you know here, these are all things given here. One is this, 0, 0, 0, 300, 0, 0, 700, 0, 0, in that way. The same thing I have created here. Okay. This you do. Okay. Okay. Now once you have created the key points, I'll create lines. I'll join this. Create lines, straight line. Join this to this to this. 1 to 2 and 2 to 3 you do. Okay. Just say okay. 1 to 2 and 2 to 3 you do. Then very important thing here, I've told you this meshing, your attribution of properties and all that very important. You should clearly make Ansys know that this is aluminum and this is steel. Okay, this is aluminum and this is steel. That means material 1 is this, real constant 1 also is this, material 2 is this, real constant 2 is this. In that way, you carefully see what I'll do. Meshing, mesh attributes, okay, pick it lines, pick this line, just say okay, material 1, real constant 1. Actually, there are two materials, no? 2 is for steel. There is also real constant also 2. There's a 2 is for steel. 1 is for aluminum. 1 is real material 1, real constant 1, and the element that is link 180 only. It's all correct. Okay, that is apply you do. Then go for this. Just say okay. Then say that this is 2. This is 2. Please understand what I've done. This you go through carefully. That means this I have assigned real constant 1, material 1. This I have assigned real constant 2, material 2. That means this I have clearly said this is aluminum with real constant as 2400 millimeter square. And this I have assigned as steel with real constant as 600 mm square. Now you see here, once you've done this, if you look at this, whether you understand, that is you have if you do this, next thing is size controls. If you go meshing, no, under size controls, manual size you do, lines, pick it lines, pick this and pick this and say okay, number of divisions only 1 you do. That means this is one element, this is one element. Totally I want to create only 2 elements here. Okay, that means you can have any number of elements. If I do 10 here and 10 number of divisions 10 and 10, 20 elements I would have created. But I have created only 1 here, that is here 1, here 1. If I had made 5, here 5, here 5 would have been created. Now I created 1. This is enough for this problem. I tell you the reason, because I want the nodal displacement at this. 1 is enough to get the nodal displacement and all that. Okay, in that way, as you see here, 2 elements I have created. And now mesh, lines, pick all or pick both the lines. Pick all you do. Now if you see here, list elements, if you go, okay, list elements, there are 2 elements, correct? No, there are only 2 elements, 1 element and 2 element. First element has real constant of 2400. Second element has a real constant of 600, real constant 600. Be careful. This you should clearly know. First element real constant 2400. Second element 600 real constant. I have correctly fed. Also, you please check whether you are correct. You have entered the correct materials. Okay, properties. All materials. See here. First element is aluminum. No, that is clearly 70E3. It is correct. This is 0.2 e to the power of 6 or 2e5. That is also correct. In that way, what you've done till now is correct. Okay, you can save up till here. Save db you can do. Okay, save db, you do this. Now once you do this, now you up till here it is called pre-processing stage. Now it is called solution phase. Define loads, apply structural displacement on key points. You click on this and click on this also, because both the ends are fixed, and all degrees of freedom you make it 0. Okay, you make it 0. In that way, this as well as this you have fixed as per the problem given. Okay, please understand, this pre-processing phase is over. Now we have come to the solution phase. In the solution phase, assigning loads and solving is solution phase. Okay, now you have force moment on key points. Let us say one key point is here, correct? Now at a distance of 300 you have a key point. There you just say okay, and in the direction you have x, it is 2e5. 2e5, that is 2 lakh newtons is applied. As you know here, it is 2E5 is the load, and if you can check here also, it is 2, 1, 2, 3, 4, 5, 2E5 Newton is applied. It is correct now. In that way, you force moment on key points. Two E5, just say okay, you say. That means the force you got 2E5. Okay, now it is the force also you got. Now you just say list loads, forces on all key points. If you see here, key point 2, key point 1 is this, key point 2 is this, key point 3, it is 0.2 into e to the power of 6 or 2E5 newtons. Okay, it is a 2E5 newtons. That is 2 lakh newtons is applied here. It is correct now. Okay, up till here, whatever you've done is correct. Okay, now once you do this, now you go for solution, solve, current LS you do. Okay, if you're done correctly, you should get the message solution is done. Okay, solution is done, you got. Okay, once you get the solution is done, we'll go for general post-processing. Please understand, now the solution phase is over. Now post-processing phase we go, where you extract the results. Now you see here, first results, list results, reaction solution you see. Reaction solution, if you see all items, okay, you see here, please understand, you have applied 2 lakh newtons here, no? The reaction is developed here and here, both in the negative direction, because this is in the positive direction. Here it will be negative. This will be acting in the negative x. Here also will be acting in the negative x. But load has been given in the positive x. This 0.13 minus I given clearly, see, minus 0.13 e to the power of 6 plus minus 69,767. If you add up these two together, you are getting 2 lakh newtons only. In that way, whatever you have done is perfect. Okay, this result, reaction, solution, all items, no. This you have to record. Okay, you have to tabulate the result. This is very important. You record this. This is one very important thing what I've asked. Next is nodal solution, DOF solution, displacement vectors up. You do this. This also you see here. Please understand, this is a very important thing. Displacement you go to get here because this is fixed. Displacement you don't get at this node 3 also because this is also fixed. Okay, this is node 1, node 2, node 3 or key point 1, key point 2, key point 3. Key point 1 or node 1 is fixed. Key point 2 or node 2 is fixed. Node 3 is fixed. Node 3 or key point 3 is fixed. Node 2 or key point 2 is open. There you see 0.23256. You should say, since I have done everything in Newton per millimeter square, this you should read it as that is displacement at node 2 I have asked, that is 0.23256 mm. Because of the load, it has displaced by 0.23256 mm. Okay, please understand that. Okay, now that is another answer what you have to record. Now next you see, next is element table you go. Element table, define table. In that way, add you do. Okay, by sequence number, SMISC1 for member force, apply you do. Then by sequence number, then LS1 also you take. This is for axial stress. You say okay. Now SMIC1 will give member force. This LS1 will give axial stress in elements. That is the two elements. Okay, just say close. Then you see here list results. Okay, element table data you see. SMISC1 and LS1 we have given. This is member force. This is member stress. Just say okay. This is another very important thing what I got. Okay, you should be in a position to comment clearly. First element is this. This is positive. This is force is 0.130 into 10 to the power of 6 and stress is 54.264 positive. That means the first member is subjected to tensile stress. But whereas the second member is subjected to force of minus 69,767 minus and stress of minus 116.28. Okay, that is negative means this is subjected to tensile stress. This is subjected to this is subjected to tensile stress. This is subjected to compressive stress because of the